I want to mention some other applications of pure functional data structures because blockchain is certainly not the only one. A commonly used application for it is Photoshop. And you go, why does Photoshop use a pure functional data structure? They have this massive data structure that is the document that they're trying to render, the image with all of its layers. And what you'd like to be able to do is have an undo button that lets you walk backwards in time. So this has got all the transformations and the result and the output of all the transformations you're doing on some complex image, quite often with many layers, with many different kinds of changes, but they only want to save the minimum amount of data. So they've gone in and they've used the capabilities of const values and constant objects in C++. It's a C++ application. So that whenever they make a change to the data for a particular image that you're working on, it does a copy constructor, and the copy constructor then produces a new copy of the data structure, but only those pieces that have changed. It's a fascinating way of going about doing this, but basically they've produced a pure functional data structure, so that if you go up and hit the undo button, you just walk back to the previous state of the data structure, and then you have the capability of redoing and walking forwards. And it comes straight out of the way C++ copy constructors and const pointers and const objects work. So I think that that's a really fascinating and interesting application. Another kind of an application for pure functional data structures that most of you have used at some point is most modern compilers involve quite complex pure functional data structures. If you look at the way most compiler construction is taught, and I believe this applies to University of Wyoming, I haven't taught it here, but an awful lot, like 2/3 of them, use the dragon-covered book. Okay, I used it. It's a fantastic textbook. Expensive as all get out, but definitely worth it. One of the few times that I'd say that a couple $100 textbook is actually that valuable and something you'd want to have in your professional career. So in any case, Aho, Ullman, and I can't think of the third author's book on compiler construction, phenomenally good book. But basically it describes a compiler as a series of steps that you go through where the first thing is you read the file, then you take the file and you scan it into tokens. The tokens have some information that goes into a symbol table. Then you take the stream of tokens, that goes to a parser. The parser uses grammar and produces an abstract syntax tree. For this entire program, the abstract syntax tree then goes on to, generally speaking, some optimizations at the level of the syntax tree. The syntax tree then goes to a code generator. The code generator generates code, and then that goes to an optimizer. The optimizer does a bunch of stuff to the code, and you finally generate out the back end of the compiler assembly language instructions, or binary in some cases. But it's a series of steps and beautifully put together, complex, lots of data structures and interesting things. And I give total credit to people who build compilers. They are complicated and hard to build. That's not the way that modern compilers work. Let's be really serious. Go into Visual Studio Code and you start entering some code and you type a little bit and you say some simple thing like string stir, semicolon. And then you say stir equals. And right there in the editor at that moment in time, in under 100 milliseconds, even though you might be working on something the size of Adobe Photoshop with millions of lines of code, the compiler responds with, oh, at this point, these are your different choices. You could be saying double quote and a constant. You could be calling a method on the string class. If you are looking at either a constructor or an assignment operator or a combination of the two. And it gives you a pop-up box. Now, if you look at the piece of code, the code is syntactically incorrect. So the compiler has to work on little snippets of syntactically incorrect code in real time and be able to derive type information and what potential future solutions are to what you're typing. And it has to do this in the context of what you've already typed. So compilers don't get the luxury of running through all the code and checking it. That luxury is the assumption that your code is actually correct, and compiles, which is probably true when you're editing, just right at the second when you're done editing, and no time before that. It's always, okay, I'm going to build something. I'm going to add this piece. It's going to have mismatched parentheses. It isn't going to have the semicolon at the end of the statement. I've got to derive the type and figure it out on the fly. So compilers use this massive data structure of pure functional data, not just for what you're typing in, but they have to keep the parse trees and the pure functional data around for the entire program and all the libraries that it is used, quite often for many different versions of the libraries, because they also have to do version management, so that if you're working on something that uses an old version of code and something that uses a new version, it has to have both, and it has to be able to derive this information on the fly in near real time. And suppose that you go into a piece of code and you change the data type of some common global header. Then at that moment in time, it has to go through all those pure functional pieces. And everywhere that data type is, it has to regenerate the tree of the abstract syntax tree and rebuild that piece. So there are huge pieces of pure functional data that exist that are changed quite rapidly on the fly. So what we're doing with blockchain and pure functional data isn't that different than a lot of other applications out there. The difference is that we're now using pure functional data in blockchains to share it and prove proofs on what it is and how it interacts at scale in a distributed system. This isn't the only kind of distributed system that can do this. Another kind of distributed system would be most distributed databases, like Google's F1 database sitting on top of its storage system. And you can also take traditional databases like Postgres that has triggers, and you can add the pure functional capability to it by implementing update triggers that ban updates, so that you can only insert and add stuff, and you can prevent deletes this way too, so that your data in your database can become pure functional and provable. And you can actually implement a decent blockchain in Postgres with only a few hundred lines of triggers and how it handles hashes and a log, and you can build a good blockchain inside the database. Let's get back to zero-knowledge proofs. There is going to be a set of reading for the zero-knowledge proofs. And I do want you to go through the reading. I've got it listed out here for the reading. And there is an overall kind of high-level description of what zero-knowledge proofs are. We're going to work through some of that, and we're actually going to look at the Shor identification protocol and how it works. That's the key piece behind SRP6A, which is what's in SSH and been used by a bunch of other applications. And there are 3 parts in this article. The first 2 parts are on zero-knowledge proof. The third part on that Medium article is on Snarks, which is a modified zero-knowledge proof that deals with the difficult setup time of the zero-knowledge construct. And these Snarks, I think, are a very valuable thing. I have yet to see if this is actually been mathematically proven to work, but it looks good to me. So I do want you to go to the reading, especially that first one, and go through it. It has a 3x3 example of what we're going to do with the mini Sudoku example. And let's move on to an example of how this all works together. We'll start with what is a zero-knowledge proof and why does it work?